Yeah. Hello everyone, and welcome to today's seminar. Thank you for taking the time to join us today. My name is Masa Sugiyama. I'm a professor at the Institute for Future Initiatives at the University of Tokyo. I'll be moderating today's session. It is our privilege to host this online seminar as part of the ongoing efforts by the Social Science Scenario Research Program towards carbon neutral society. This initiative, this seminar is supported by the Japan Science and Technology Agency. So our focus today is on the future of buildings, and it is very fitting to talk about this topic on a hot, humid day like this. Whether it is related to climate change or not, it is very humid, and we are in a building with air conditioning. At least we are. And I think it's critical to think about how we can reduce emissions and material demands and energy from buildings while still ensuring the buildings serve people's needs and support well-being. And this is a really pressing issue, not just here in Japan, but globally. So to talk about this, it is a great privilege to welcome Dr. Alessio Mastrucci from the International Institute for Applied Systems Analysis, or EASA. He brings deep expertise in modeling both energy and material demands particularly for the building sector. We actually happen to be close collaborators with each other, so we do a project together on the demand side edits. So it is wonderful to have here. He happens to be visiting Japan to attend the International Energy Workshop that took place last week in Nara, and he's now visiting us here in Tokyo. So a few housekeeping announcements. So this session will run for about an hour, and Alessio will talk for about 40 minutes, and we can have questions and answer sessions. Because of the logistical issues, the audience is encouraged to type in their questions and comments in the Zoom chat. This is not a standard webinar. We are using the function of a Zoom meeting as if this is another kind of webinar, so please do understand that. And if you have any trouble, you can also type in your comments or issues into the Zoom chat, so please. So without further ado, I am very pleased to invite Dr. Mastrucci to start his presentation. So Alessio, over to you.
Thank you very much, Maza, for your kind introduction. It's also a privilege and honor for me being here at the University of Tokyo today and having also the opportunity to give this seminar. Let me start sharing my screen. Okay, now, yes, the presenter mode is there. Right, so my presentation for today has a title, Low Energy and Material Demand Futures for Buildings, Challenges and Opportunities. My name is Alessio Mastrucci. I'm a senior research scholar at the International Institute for Applied Systems Analysis, IASA, based in Austria. I will start just with a few words about IASA. So we are an international institute based in Austria, and I'm part of the Energy, Climate and Environment program. So as part of this program, we contribute to develop scenarios to understand also the potential roadmaps to meet simultaneously sustainable development goals and climate targets. So you can see here at the bottom a photo from our main building, which is the Schloss Luxembourg, located in Luxembourg, which is a small town close to Vienna. And as you can see on the left side, so we have a strong focus also on global challenges, and we use integrated assessment and modeling. So these are complex models that try to capture also system interaction and also seek for solutions that can be effective also across different sectors. So our main model is called MessageX Globium. So this is an integrated assessment modeling framework focused on energy, and you can see here that we have also many interlinkages that allow us to capture also interaction between the energy system and the end use sectors, as well as land and climate and other different aspects. I'm coordinating the Sustainable Buildings team in the EC program. So we focus here specifically on the building sector, and also try to understand what are the options for mitigating emissions from the sector, while also improving the well-being of population. Yes, with this, I can start with the actual content of the presentation. I will start with a brief introduction about the challenges and opportunities in reducing energy and material demand in buildings, and then present a little bit on the modeling, how to model building scenarios to basically provide support for decisions of policymakers, and then present some of the most recent scenario analysis works that we have been carrying out at YASA. So let's get started. And indeed, buildings are a very important component of the built environment, and we typically spend more than 90% of our time inside buildings. So this, I think, highlights how important buildings are. Of course, this can also change based on different world region and climate, but in general, buildings support our activities and well-being, and therefore play a very important role for us. But also they're responsible for high energy and material demands. And this is through the different stages of the life cycle of buildings. So if you start from the construction, so there is a very important impact from the materials that are produced for the buildings and from their construction. And then over the use of the buildings, of course, we require energy for space heating, for cooling buildings, and also for using the appliances that we have inside those buildings. And then we go until the end of life, where the buildings are dismantled. So in general, buildings account for more than 20% of the global greenhouse gas emissions. And even though a big part of those emissions are related to the energy used in buildings during their operation, there is still significant amount of embodied emissions. So 18% as estimated by the latest IPCC report, which are due to the material part, so the material produced for buildings and the construction stages. But there is also here an important opportunity for mitigating emissions in buildings, and the latest IPCC report on mitigation of climate change estimated a potential of 61% by 2050 compared to a baseline scenario for reducing emissions in the building sector. However, getting to this mitigation potential is quite challenging. And if we look at the numbers on the global energy consumption in the building sector, we can see that despite recent improvements in the energy efficiency of buildings, the energy consumption globally has not really been going down at all. And this is because if we look, for instance, at the floor area, so we have been experiencing a growth in the floor area, so in the stock of buildings over time. And this is especially strong in the emerging and developing economies, where the building stock is growing more rapidly, as well as we have been using also more intensively energy for the operation of those buildings. And so those energy efficiency improvements have not really corresponded so far to absolute reduction in the total energy demand for the building sector. And this means also that we still remain off track compared to what are our mitigation ambitions for the sector. So why is the building sector challenging? Because it's of course quite a complex sector. It's very much linked to the different contexts and climate. Very heterogeneous. We have many different types of buildings with different requirements and different options for reducing energy and material demands. And many actors that work or use buildings, starting from the households living in the residential sector up to the constructors and other companies, and also all the way up to the policymakers that decide on the building regulations and policies. And challenges related to buildings also differ very much in different world regions. In the global north, we have to deal with the existing building stock that is often also quite energy inefficient, and therefore the mitigation potential mostly relies on renovation of existing buildings to improve their energy performance and reduce energy and material demands. While in the global south, there is an unprecedented stock expansion expected to come in future years, and this is due to population growth in many regions of the global world, but also increase in the building size as also affluence is growing. But at the same time, there are also challenges related to the access to decent housing and to permanent buildings. And therefore, there is also here an opportunity actually to improve the well-being of population by providing access to decent housing and decent living standards, while also promoting low carbon technologies for the future buildings that still need to be constructed in many world regions. And I will introduce now briefly the EDITS network that was already mentioned by Maza. So EDITS is a big network of around 200 members from many different world regions, and this is coordinated by the RIGHT and YASA institutes and founded by the Ministry of Economy, Trade and Industry, METI, in Japan. The focus of this network is about the potential for demand-side solutions, so for energy and material demand reductions, which can be indeed supported by technological and social innovations. And I'm showing here on the right a figure from a paper that was led by Maza and was published last year, which is showing also the multiple benefits that reducing energy and material demand can trigger. So, of course, we can reduce embodied and operational emissions of buildings, but there are also many co-benefits linked to reducing energy and material demands, which start also with improving the health and well-being of the population, but also reaching a more equitable society and also maybe contributing to the economy and to energy security. And when it comes to the building sector, in our recent research work in the EDITS project, we have been trying to map what are the most promising strategies and opportunities to get to low energy and material demands. And we started by conceptualizing these strategies along this triangle. So these three different dimensions of transformation: social, behavioral, infrastructural, and technological. And I will briefly introduce them to start with. So I will start with the technological transformation. So maybe this is the dimension we are more familiar with. So when we talk about energy efficiency improvement in buildings, so there are options that are now well known and already applied in many world regions, which basically allow for reducing, in the first place, the energy demand related to buildings by, for instance, insulating the building shell or replacing windows with more efficient ones. And this enables reducing already the demand for instance, for space heating and cooling without the buildings, while keeping comfortable temperatures and humidity and inside the buildings. The second step regards the energy efficient appliances, heating and cooling system, and so we can improve the energy efficiency of those buildings. So you see, for instance, here the picture of a heat pump, which also allows basically for further energy reductions. And finally, we can think about the building as a whole and also integrate renewable energy sources to also integrate with the buildings and complement those energy savings also with clean energy supply. But there are also two other dimensions which are very important. So the first one regards the infrastructure. And so if we think about the way cities are built and the urban form, we can already contribute to reducing this material and energy demands by designing those urban settlements, for instance, in a more compact way, so that we can have more efficient buildings and also reduce the floor space. So we have, for instance, in Europe, a problem with vacant buildings that could be to some extent reused, so to avoid the construction of new buildings and basically optimize the occupation of existing ones. And this goes also through, for instance, adaptation and flexible reuse of buildings, but also materials are very important, and switching to low carbon materials or bio-based material could provide also with an important contribution to reduce embodied emissions. And finally, also community approaches can help there. The third dimension, also a very important one, is about the social behavioral transformation. So we can all of us can make a contribution to reducing the energy demand of buildings by with our behavior and also lifestyle choices, and also, for instance, reducing the set point temperature for heating can contribute to also reduce that energy demand. And there are also many different types of strategies and policies which can contribute also to inform people and make more aware of more low carbon lifestyles, and therefore also engaging with citizens with more participatory approach and help basically also with just behavioral measures to reduce those energy demands. I wanted also to highlight that there are some important mega trends which also are cross-cutting across these dimensions. And the first one is, of course, digitalization. And so digitalization can directly and indirectly influence those material energy demand in the building sector. And since there is also a risk of increased energy demand because of digitalization, this is very important to take care of, but there are also some opportunities, for example, in using smart meters and building information modeling to also optimize some processes, operation in buildings, but also design of buildings, and contribute to reducing energy and material demands. Sharing economy is another important one, where we have strategies such as co-housing and co-working or sharing of appliances that could also help. And finally, circular economy can also contribute here to material and energy demand reductions when we look at the lifetime of buildings. Finally, there is also decent living standards. So these are also very important. So these are the requirements to support the well-being of population, and there are important aspects related to the building sector, such as durable and affordable housing, sufficient space, and access to clean and affordable technologies that are very important to consider when thinking about mitigation in combination also with sustainable development. And I will come back on this point. So this was a brief overview of basically what are the key strategies and what we can do towards to achieve more sustainable building futures. And now I will move to talk about modeling, because modeling is the way we can understand implications of these strategies and also understand the potential into the future. And this is just a brief overview. So this building sector modeling has been now for for like already a couple of decades, has been already experimented and implemented by many researchers. Focusing here on more large scale for supporting the decision of policymakers at different levels. And there are some established approaches here. In general, we have these three main categories. So the top-down approach is more aggregate and high-level approach, whereas the bottom-up here on the right is much more detailed and can provide more also thorough assessment of the techno-economic potential of different strategies for the building stocks. And then the combination of these two approaches can result also in hybrid approaches, which can combine basically the strength of those two. So current modeling has been focusing prominently also on the technology side, but there are also different layers which are very important here, and especially as I will show in the next slide, we have been surveying different models from the EDITS network and focusing on the building sector, which has highlighted indeed that while there is a strong focus on technology and technological innovation on many of them, there are still some gaps, especially on the representation of socioeconomic aspects and dynamics, as well as urban form and other aspects related to infrastructures that would need to be bridged in order also to improve the capacity of these models to also being used for providing support to different types of policy. And also the global south has been also underrepresented or represented in a more simplified way in this set of models. So here is also a suggestion and to focus more on the different world regions to really support the mitigation strategies in different world areas, as well as sustainable development, and look also into cross-sectoral linkages. This is Message X Buildings is our building sector model we have been developing at IASA, and this includes both models to assess energy demand and material demands in the building stock, and also for household appliances. And we tried here, while focusing on the global scale, to also keep a high level of resolution and detail to account for the differences in the building sector across different socioeconomic groups, building characteristics, and different world regions. And we have established a connection also with the supply side model, Message X Globium, which is indeed focusing on the energy supply system. So to capture also the key interlinkages between the demand side and the supply side. At the core of this model, we have two key components. So the first one is a model called Chilled, which is used to estimate energy demand for space heating and cooling globally, also with quite high spatial resolutions. And then we have a second component, which is called Storm, which accounts for the future stock turnover. So how the building stock will evolve into the future in different scenarios. And here we also have embedded a set of discrete choice models. So these are logic type model, which represent the decision of households in energy efficiency investment. So this is a simulation-based approach. And as you can see, we also take some inputs from Message when it comes to energy price and emission factors to basically account also for them into the different type of future scenarios. So at the core of the model, there is a description of the building stock into a set of different building groups and cohorts. And we account here for different building types and also different periods of construction of buildings, as well as renovated and newly built, and try to represent also different energy carriers and different materials. So each of these different categories is represented by archetype buildings. and we can therefore upscale also results from the single building cohorts by to the entire stock by accounting for how many buildings of specific types or specific cohorts are present in the stock in different time step over the future. As you can imagine, for the global implementation, we used an extensive set of data to inform the model, and we try to rely on different census data, statistical data, and building libraries from different world regions. And we typically use this model to develop scenarios up to 2050 or also to the end of the century, accounting for the evolution of the building stock and then projecting energy and material demands. So let's now move to some more concrete example of scenarios that we have been developing. And I will show first some scenarios at the global level and then also some national and regional scenarios. Let me first introduce this shared economic pathways. So the SSPs, this is the framework we use as basically a starting point for our scenarios analysis, and is a broadly used framework in the context of integrated assessment modeling. There are 5 main SSPs, which you can see here in this matrix, and we start often from the SSP2, so-called middle of the road. So this is a scenario describing continuation of current trends with medium challenges both for adaptation and mitigation. And from here, basically moving now to the bottom left corner, we have a scenario SSP1 called sustainability, which has a quite low challenges both for mitigation and adaptation. And this is associated also with lower population growth, higher urbanization, and higher GDP rates, and quite a direction of this scenario towards sustainable development and also technological innovation. At the other end of the spectrum, the SSP3 scenario, so the regional rivalry, has high challenges both for mitigation and adaptation, and this is characterized by higher population growth, lower urbanization, lower GDP. So we typically use some basic drivers like population, urbanization, GDP, and inequality to describe potential socio-demographic developments associated with this set of scenarios. And here I'm showing results from a paper that just got published a few weeks ago, which is about understanding the potential for policies on the demand side for the residential global sector to achieve mitigation. This is focusing on the residential sector and on space heating and cooling. So you can see here on the bottom left, the set of scenarios we have been investigating, which cover quite a broad range of policies, starting from activity reduction. So here we have floor space reduction and also more conservative set points for heating and cooling. So this is related also to the behavioral change I mentioned earlier. Then the ELE scenario is related to electrification and phase down of fossil fuels. And the tech scenario is related to technological improvement and especially energy efficiency improvements. And then we combine all of these scenarios in the whole scenario for the demand side. And then we also have a supply side with this climate policy scenarios, with the NPI scenarios, which assumes a continuation of current policies, and the 1.5 degree scenario, which represents more ambitious scenarios achieving ambitious climate target compliant with 1.5 degrees. So you can see here on the left the results for energy demand in different world regions. So in Europe, the US, other global north, and then in China, India, and other global south regions. And as we can see, for cooling, so Maza referred to a hot sunny day here in Tokyo, but with increased access and growing building stock, in the global south regions, we will have a very massive increase in the energy demand for cooling in many of these regions of the global south. And this is not yet accounting actually for the climate change which could further exacerbate this. But you can also see that actually by implementing this energy efficiency and activity reduction strategies, the energy demand for cooling can be also significantly reduced. Whereas for the heating part in red, this is now mostly due to the use of space heating in the regions, in colder regions, so mostly in the global north, and is expected to basically not increase that much in most of the regions, or even to reduce under energy efficiency improvements over time. But it's still quite a higher share of the energy demand for thermal comfort in many world regions. So you can see here on the right how this corresponds to different emission trajectories, where we have this emission growing in the reference scenario. And then with the implementation of demand side strategies, this can be reduced down to almost 60% in the NPI all scenario. But to really get closer to net zero, we need to combine also the strategies with also supply decarbonization. So in the 1.5 degree, we have decarbonization of electricity and district heating, and complementing demand side strategies with this supply side decarbonization is the most effective to really get close to net zero until 2050, which also highlights the importance of demand side strategies complementing supply side decarbonization. But despite this stark growth in cooling demand, there are still big gaps in access to thermal comfort in many world regions. And this is because so a big part of the population don't have access to cooling systems or even to electricity in some world regions, so they would not even be able to run a fan to basically improve their thermal comfort. Or they also live in buildings with poor quality, which also provides weaker and a worse thermal comfort inside the buildings. So in this work, we have been trying to estimate what we call the cooling gap. So this is defined as the population without access to cooling where needed to provide basic thermal comfort. And we have been estimating also how the amount of population affected by the cooling gap will change into the future. And we estimate that between 1.9 billion people and 5.1 billion people in the global south will be affected by the cooling gaps by 2050. So this is quite a big number. And of course, this also has a huge implication for the health and for the well-being of the populations. But you can see how already like different socio-demographic patterns can also influence the magnitude of the cooling gap, where, for instance, in SSP1, we have less people affected because of the lower population growth and also because of the higher affluence, which makes people more in a better position also to buy cooling devices. But the other part of the story is also that if we want to close this cooling gap and so to provide thermal comfort universally, so to the entire population, this would require quite a significant amount of energy. And here is where actually the demand side strategies, so improving the thermal characteristics of buildings by providing, for instance, shading and natural ventilation, as well as more energy efficient cooling system, can contribute in bringing down those energy demand and also contribute to the mitigation targets. This is another work we have been carrying out with colleagues from the University of Oxford, in particular with Hazel Pettifor and Charlie Wilson. And I mentioned earlier about the potential for behavioral and lifestyle change. And here we have been linking our building stock model with a framework for understanding also the the potential for lifestyle change using, which is based on empirical survey data. And so this is called the LIFE model, which was developed by the University of Oxford and can represent also different groups of households in terms of lifestyle change and also their decisional process. So how they make decisions toward more low carbon lifestyles. What is interesting is that the empirical work highlighted that 4 lifestyle groups could be identified consistently in different world regions. And this you can see here as the resourceful, active, constrained, and cautious groups. So the resourceful and active are more prone basically to changing lifestyle towards more low carbon behaviors, whereas the constraints don't have the means to make those changes happen. Typically, they are lower income households, or the cautious have the mean but not the will to make the change. And what we try to do here is basically to bring these 4 lifestyle groups into the model and to understand how they interact also with the context and with the building stock over time. And so we developed a set of scenarios where we try to understand also the potential for shifting those lifestyle changes with strengthening the cognitions and also shifting the values of these household groups. And we could highlight here that there is a potential for the constrained and cautious groups to further reduce energy demand in their homes by changing the set point temperatures, but also uptaking more advanced renovation options to reduce the heating demand. And globally, so this could result in reduction in energy demand in the order of magnitude of 8-9%, which of course is not negligible if we want especially to look into more ambitious climate goals. And finally, just a couple more of examples, more at the regional or national level. So this is a study which was led by Luca Vivier and tried to understand the potential for different policy options in the European Union, encompassing also carbon taxes, heat pumps, and energy renovation. One interesting dimension here beyond the CO2 emission reduction was also the cost dimension. And we made an assessment of the cost benefits associated with these different strategies, highlighting that, for instance, renovation is quite costly. And so there is quite some investment cost associated with that, whereas the cost benefit ratio is more favorable for heat pumps. But at the same time, renovation can be also associated with alleviation of energy poverty. And so targeting energy renovation for older buildings and especially for energy poor households can also have quite a significant impact on alleviating this issue of energy poverty and can be an effective strategies in such a context. The last example I wanted to show is from a project called Circular. So this is a Horizon Europe project where we investigate the potential of circular economy strategies in contributing to mitigation, in this case in the building sector. And we focus here not just on energy demand, but also especially on the material demand. And this is a study we carried out for China, which of course is one of the countries which is contributing the most to embodied emissions for building construction due to quite intense construction activities. And we show here how some demand side option to reduce material demands, including reduction of floor space, for instance, switching to different building types and co-housing and co-working, but also switching to more low carbon materials and wood-based construction and extending the lifetime of buildings, which is quite short in China, could contribute to reduce the material demand of more than 60% by 2060 compared to a reference scenario. And this has quite important implication also in reducing the embodied emission parts of buildings, which would be very important, especially in the framework of more ambitious mitigation policies. And we show that in the case of China, around 60% of the embodied emissions by 2060 could be reduced compared to a reference scenario by implementing these strategies. And this corresponds also to 24% under current policies of the total life cycle emissions for the building sector. And so also thinking about the massive expansion of the building sector, which is expected in many countries in the global south, this is a call also for the importance of looking into materials and not just energy to really achieve the climate mitigation goals. And with this, I would like to conclude my presentation. And just a small advertisement at the end. So it's about the Young Scientists Program at YASA. So every summer, YASA is hosting 50 doctoral students to join YASA and to work together on a research project. So this is a call for joining this program, and the deadline for application is usually around January for the next year. So this is also an invitation to please get in touch in case you have any interest in this program. And yes, with this, I would like to close my presentation, and thank you very much for your attention, and looking forward to your questions and comments. And thanks very much for hosting me, Masa, and the University of Tokyo. Yes, it's been a great pleasure. Thank you.
Yeah, thank you. Alexia, it's on the presentation. So, so now the floor is open for questions and comments, and because of the logistical issues, so please type in your questions and the comments in the Zoom chat, and I think it will take some time. So while and also for those who are in the room, you can raise your hand and ask questions. But I think while people are typing in or thinking about questions, I have some initial questions. Could you go to slide 23? And we've been talking about, you have been emphasizing demand side solutions and the demand side interventions. But I think this could be a new concept to some some members in the audience. So if you could go to slide number 23. So I think the electrifications are using heat pumps. That's fairly easy to understand. But what else are you thinking, especially if you say ACT, in the lower left panels, activity reduction? What are you thinking about in this context, and how large can they be? What is your assumption? Just briefly, and also just because people may not be familiar with, Japanese are familiar with the cool bits. I think it's 20th anniversary or something. So we took away the necktie ties, and we used to wear neckties even in the middle of the summer, but now they're kind of gone. But I think there are other things you're thinking of. So could you explain that?
Of course. Thanks, Masa, for your question. Indeed, I think the cool biz is a very important example here, where of course the dress code was relaxed in office buildings to allow for using a more moderate set point for cooling, and then raising a bit the temperature. So this is exactly the type of policy which is included in the activity reduction, and could especially, I think, make an impact in the global north, where often those temperature set points are set up in a way that is too aggressive compared to what we really need for our thermal comfort. And so reducing the set point temperature for heating and increasing a bit the one for cooling still providing, sufficient thermal comfort could contribute also in saving energy. Under activity, we also include floor space reduction and shift in building types. So this means that some of the spaces we use in buildings could be shared by more people. For instance, in the residential sector, even there could be an option for co-housing, where, for instance, we could think about some residential complex where households would accept basically a bit lower floor space in their homes, but they still would have plenty of common rooms, like common living rooms or kitchens or storage rooms, which could be shared with other neighbors. And this would basically enable reducing floor space, as well as maybe even enhancing the social interaction with our neighbors that sometimes we don't maybe see very, very often. So this is the type of measures that we included in the activity. For electrification and fuel shifts, so indeed, Maza was mentioning about heat pumps. So this is indeed a very good way, because these are very efficient systems, and once we shift to electricity, it's also easier also to use renewables, basically, to then provide supply for electricity. But here, especially for the global south, but also for many world regions, we need to think also that there is still large use of fossil fuels in many instances, and also then phasing out those fossil fuels could help also in reducing energy demand while using more energy efficient systems.
Yeah, thank you very much. Speaking of heat pumps, well, I think that some idea came up to me, but that's not relevant today. There's one question in the chat, so let me read it aloud. So thank you very much for your insightful presentation. When considering the embodied CO2 emission from material flows, I thought that country where products were manufactured would have a significant impact. And so Alicia, how do you consider such international material flows?
This is a very important question. Indeed, this is something we are currently working on. I think when it comes to the building sector specifically, we need also to make some distinction, because there are also many of the bulk materials. If you think about cement, for instance, are usually locally produced or produced often in a quite close location. But of course, it's not the same if we think about other materials, which could include, for instance, steel, other metals, and plastic. And indeed, I think it's very important to account for the site of production of those materials. And we are working on implementing also this part in our framework, so to better account also the trading and where basically those materials are currently produced, and therefore also where emissions for producing those materials are happening, so that we basically don't just shift our emissions to different regions, and suddenly we have, yes, decarbonization in our focus regions, but some burdens somewhere else. So thanks very much for that question, very important.
Yeah, so thank you very much. And maybe it's a bit related to this previous question. So I have another question, and that is related to how you integrate different types of models. So in one of your slides, you showed the message IX macro and the message IX buildings, and I see you are sort of going beyond the traditional integrated cement modeling sort of a realm. So, and IM is integrated cement models kind of started off from the energy systems modeling, if you will, and now you are doing it. But could you, briefly talk about how you go about it? You already showed it, but I think because I'm just curious how long it took to build up the system, and of course, I know a little bit about the message IX, but and also I'm just curious because you have another project, circular, and I just wonder you have touching on the life cycle assessment or other types of modeling or analytical methods, and I think this is a very great, but I think at the same time this looks a lot of work to me. So I just would like to know how challenging it is, or how maybe rewarding it has been to tackle this from multiple perspectives.
Right. Yes, this is a very good question, Maza. So indeed, I think you mentioned about integrated assessment modeling. Traditionally, this type of modeling has been focusing on the energy supply side. But of course, we need also to include the demand side, because there are many policies and a lot of effort going on in the different end-use sectors, and we need to better understand what is the interplay between those sectoral policies and also the more energy supply related ones. And so in our case, but I think it's a general trend in integrated assessment modeling, the traditional models has been expanded to also account for the end-use sector in a more detailed way. And this means also bringing in sector-specific models which can answer those policy questions, providing more detail, more sectoral detail there. So there are different ways of getting there. So there are different levels of coupling that could be achieved, starting from soft coupling, which is mostly about data exchange between models, going all the way to more hard coupling or even model integration, where the models get more tightly linked and running together or in an integrated way. In our case, the linkage between our sector model and the energy supply system is more of a soft coupling type. So the model can exchange data. So we established a common data format, and there can be feedback in providing data from the sectoral model to the supply side model and vice versa. But there are also other examples of more integrated coupling. This, of course, comes also with some challenges on the how to implement the coupling. And in general, even if soft coupling is maybe more simple, there is still challenges about the data exchange, and so making sure that the different models can communicate between each other. So this takes, of course, time and effort, but I think the soft coupling is maybe a solution that can be working in many instances, because it's a bit more simplified compared to maybe more fully integration between the models or hard coupling type. But I think this is very much dependent on the type of application and goals for the coupling itself.
Yeah, thank you very much. And so please.
Yes, thank you very much for this very, very interesting talk. Actually, I have a couple of questions. I think maybe I start with one, and then some others can also have some more questions. My question is about aging societies. And I mean, we hear in many ways that this is posing us many challenges. And I can imagine, and just from observation, it kind of makes sense. Like if you're getting together as a couple and have some children, you try to have the biggest apartment you can afford. And at some point, the kids grow old, they move out of the apartment, but you may not really move out of your apartment. And you occupy this apartment that is essentially as large as it was meaningful at the time. So are you able to capture this in your models? And if you are able to capture this in your models, what kind of policy recommendations can you see that can be made to kind of approach this kind of situation? Because I can imagine that it's very difficult to influence.
Thanks so much. Yes, thanks for this very important question. This is interesting, something we have been discussing just before the seminar and this webinar with Mazen-san and with Tao here, so colleagues from University of Tokyo. We are collaborating in this indeed on modeling scenarios for the residential sector in Japan, where aging is, of course, a very critical topic. And indeed, I think that the strength of the bottom-up approach is that it allows for including also more dimensions, especially here the socio-demographic, socio-economic dimension. And one could then think about including different types of households in the model, so that one can, on one end, also model the different preferences and behaviors of the different household groups, but also understand which targeted policies could be implemented and effective to address specific issues. And especially for when we think about indeed elderly households, there is often an issue of quite big house size, which is maybe not even needed by the person. It's just a legacy basically of having first a family and then living alone or in a couple. And there are examples of policies which target exactly this point where, for instance, there are some moving bonuses where elderly households can maybe move to a smaller place. Of course, this might be associated also with many benefits, like lower running costs for the home, or I don't know, less cleaning efforts. And there might even be a chance actually to maybe more collective type of living, where maybe elderly households can come together and help each other. So I think these are very important types of policies that could be and should be represented more in our models. So to also show that it's possible at the same time to improve maybe the health and well-being of specific segments of the population, while reducing also the demand for energy and materials, maybe with more, higher occupation rates and less vacant floor space. So thanks for this question.
Yes, for the answer. Yeah, vacant space is that's a very big headache for Japan.
Yeah.
And indeed, there are lots of there's an increasing number of vacant houses on that. So yeah, I mean, purely economic perspective, that's a big problem. Any questions from the floor? Or, yeah. I think so. I have one last question, and probably it's getting to the end of time. What would be so we talk a lot about policies. We do modeling, and not for the sake of modeling, but we do modeling for to provide advice to policymakers and the stakeholders and the business people, right? So, and what would be your policy recommendations or policy prioritized policy recommendations? And I think you touched on the European recent paper that came out in Nature Climate Change, a very high impact journal, and I think in that paper you emphasize the heat pumps, right? So what are the sort of the prioritization of policies, for countries like Japan?
Yeah, well,
it's difficult to generalize, of course, but your gut feeling is what would you say?
Yes, thanks. This is indeed quite a big question, but I think the learning from the modeling exercise we have been carrying out is actually that I don't think there is a one size fits all, because as I mentioned at the beginning, the building sector is very heterogeneous, and we need to keep in mind actually these differences, both in the building types, but also in the context and in the people that are using or living in those buildings, to really come up with effective policies. And I think thinking about indeed targeted policies that can address specific challenges is very important in this space, so that the most effective strategies could be thought of, and especially the linkage also with other challenges, and so how we can best combine also different priorities, not just in terms of energy demand or material demand reduction, but also in terms of sustainable development, well-being of population, and socialization. I think this is really key to prioritize the policies and really have broader impact out of them beyond what is just the climate mitigation effect, which is of course key, but I think it's even more can be even more impactful. So these strategies can be even more impactful when also the co-benefits associated to those strategies can be fully developed.
Yeah, thank you very much. And maybe I asked to like the question to the end. But I think it's we are at the top of the hour, and I think yeah, I said it's going to take place in 1 hour. So this is the seminar is coming to the close. So thank you again. Thank you very much for joining us for this online seminar. And please, let's give another round of applause to our speaker, Dr. Alessia Masrici, once again. So thank you very much.
Thank you very much.